Hello friends, welcome back to my YouTube channel. So in last video we have seen a problem of Kani's method. Today we'll see one more problem of Kani's method. How to analyze the problem by using Kani's method. So this is the given problem. Analyze the continuous beam shown in figure by Kani's method. So as usual our first step is to find out the fixed end moment. This is also same as we have already calculated this fixed end moment in slope deflection method as well as moment distribution method. For span AB, we have the formula MFAB is equal to minus WAB square divided by L square. Substitute all the value, it will come out as minus 1.5 kilonewton into meter. Similarly, for MFBA, we have the formula WA square B divided by L square. Substitute all the value, it will come out as 4.5 kilonewton into meter. Similarly, for member BC, it is carrying the point load. MFBC is equal to minus WL divided by 8. Substitute all the value, it will come out as minus 3.75 kilonewton into meter. MFCB is equal to, here the formula is same, only sign will change. Here negative, here positive. So substitute all the value, it will come out as 3.75 kilonewton into meter. Similarly, for member CD, it is carrying the UDL. For that we have the formula MFCD is equal to minus WL square divided by 12. Substitute all the value, by simplifying it will come out as minus 3 kilonewton into meter. Similarly, for MFDC, we have the formula WL square divided by 12. So it will come out as 3 kilonewton into meter. So our second step in Kani's method is to find out the rotation factor. To find out the rotation factor, one table will come. So this is the table. First column it has the joint and second is members, third is stiffness, it is denoted as K, and summation of K and RF. Rotation factor, we have the formula minus 1 divided by 2 into distribution factor. So to find out the distribution factor, we have the formula K divided by summation of K. We'll see. So joints, how many joints we have got? Here we have got two joints here, joint B as well as joint C. For joint B we have the member BA and BC, and for joint C we have the member CB as well as CD. So I have written same thing here. So now we'll see. For member BA we have to find out the K stiffness. For BA, see here BA our foreign is fixed end. So fixed end we have the formula I divided by L. We need to put this formula to calculate the stiffness. BA we have the formula I divided by L. So here I for member BA, I is 2I and length is 4 meter, and substitute here I is 2I and length is 4 meter. By simplifying it will come out as 0.5I. Similarly for member BC, so BC it is continuing. So when our far end is continuous, we have to use the formula K formula I divided by L. Again same formula we need to use. BC is equal to I divided by L. So I for span BC is 3I and length is 3 meter. So put this 3I divided by length is 3 meter. Simplifying it will come out as I. And for CB member, for CB far end is continuing, so again we need to use this formula I divided by L. So I for CB span is 3I divided by length is 3 meter. So it will come out as I. And for CD here far end is simply supported, it has the roller. So when our far end is simply supported, we need to use the stiffness formula 3I divided by 4L. We need to use this formula to find out the stiffness of simply supported 3I divided by 4 into L. So 3 into I for this member CD is 4I and length is 3 meter. I is 4I, length is 3 meter. Length is 3 meter into 3 divided by 4. It is as it is. So 4 will get cancelled. 3 will get cancelled. Remaining is only I. 1 I will be remaining. So now we need to summation of k means we need to add these two 0.5i and 1i. It will come out as 1.5i. Similarly for this I plus I 2i. Now we need to calculate the rotation factor for member BA. We'll see rotation factor is equal to 1/3 of distribution factor. For that we have the formula k divided by summation of k. So here k is 0.5i divided by summation of k is 1.5i. It will come out as minus 0.166. Similarly for member BC, rotation factor is equal to minus 1 divided by 2 into I divided by 1.5i. It will come out as minus 0.333. Similarly for member CB, rotation factor is equal to minus 1 divided by 2i divided by 2i. It will come out as minus 0.25. Similarly for this, it will also come as minus 0.25. Both will come same. This is how we need to find out the rotation factor. Our third step is to find out the contribution. It is denoted as m dash. It is also called as the rotation moment. So rotation moment, for that step number 3, we need to draw the box like this. Wherever joint is there, we need to draw boxes like this. So now first thing what we have to do is write down all the fixed moments here. So fixed moment of AB we got was minus 1.5 and fixed moment for BA we got was 4.5. Write it here. And for BC we got was minus 3.75. For CB we got 3.75. For CD we got minus 3 and for DC we got plus 3. So now what we have to do is add these two and write it here center. So 4.5 minus 3.75, it will come out as 0.75. Similarly here also add these two and write it here. 3.75 minus 3, it will come out as minus 0.75. And now what we have to do is here in this box we have to write down the rotation factor what we have calculated. Here rotation factor for BA we got was how much? We got was minus 0.166. Rotation factor for BC, write it here, we got minus 0.333. And rotation factor for CB we got was minus 0.25. Write it here. And rotation factor for CD we got minus 0.25. So I have written all the value. Next what we have to do is add minus 0.166 into 0.75 plus this foreign movement, this one and this. Initially we need to take the foreign movement is 0. So only add these two, minus 0.166 into 0.75. It will come out as minus 0.1245. Similarly for BC, minus 0.333 into 0.75. For this value and this value is 0, only add these two. So it will come out as minus 0.333 into 0.75. It will come out as minus 0.2497. So now for CB, add this one into this one plus this one, and here is 0. So minus 0.25 into minus 0.75 minus 0.2497. So if you do, it will come out as 0.2499. Similarly for CD, this one into this one and this one and this one we need to add. So minus 0.25 into minus 0.75 minus 0.2497 into this value is 0. So if you do, it will come out as 0.2499. So similarly we need to do the second iteration. For that, this value into this value plus this value. So if you do, it will come out as minus 0.1659. Similarly for BC, this value into this value plus this value. If you do, it will come out as minus 0.3329. For CB, this value into this value plus this value. It will come out as 0.2707. For CD, this value into this value plus this value. It will come out as 0.2707. So now for next we need to do the one more iteration. This value into this value plus this value. It will come out as minus 0.1694, and this value into this value plus this value. It will come out as minus 0.3398, and for this value into this value plus this value, it will come out as 0.2724. For this value into this value plus this value, it will come out as 0.2724. So now we will do the one more iteration. This value into this value plus this value, it will come out as minus 0.1697. Similarly for CB, this value into this value plus this value, it will come out as minus 0.3404. Similarly for this value into this value plus this value, it will come out as 0.2726. Similarly for this value into this value plus this value, it will come out as 0.2726. So see here, almost we got the similar answer. It is very close to this iteration 3rd and iteration 4th. So we got the nearest value. So now we have to stop here. When we get the nearer value or the value is very close to this one, we have to compare these two. So see here, the value this value is very close to this value. So now I am stopping here. So this is our rotation moment, final rotation moment value. So now we'll see the this value final moment. Our step is to find out the final moment value. For that we have the formula MAB is equal to MFAB plus 2 into near end rotation moment plus 1 into far end rotation moment. So I'm go with this method. So 1 2 is nothing but our member numbers. So MF12 means fixed end moment of AB. So I have written here all the fixed end moment of corresponding members. So now we'll one by one we'll do. So fixed end moment of AB is minus 1.5, and here 2 into M dash 1 is nothing but rotation moment of AB. So rotation moment of AB we don't have the value, so keep it as 0, and M dash 21 is nothing but rotation moment of BA. So rotation moment of BA we got was minus 0.1697. So substitute that value here, minus 0.1697. So now add these three. So it will come out as minus 1.66 kilonewton into meter. Similarly for BA, fixed end moment is 4.5. 2 into rotation moment of BA is rotation moment of BA we got was minus 0.1697. So M dash 21 is nothing but rotation moment of AB. So we don't have the rotation moment of AB, so keep it as 0. So add these three value, it will come out as 4.16 kilonewton into meter. So similarly for BC, this is the fixed end moment, and 2 into rotation moment of BC we got was minus 0.3404. So minus 0.3404. Now M dash 21 is nothing but rotation moment of CB. So rotation moment of CB we got was 0.2726. So write it here, 0.2726. Now add these three, it will come out as minus 4.15 kilonewton into meter. Similarly for CB, this is fixed end moment. 2 into a rotation moment of CB we got was 0.2726. 0.2726, and rotation moment of BC we got was minus 0.3404. Minus 0.3404. So add these three, it will come out as 3.95 kilonewton into meter. For CD, this is fixed end moment. C into 2 into rotation moment of CD. 1 2 is nothing but here. CD value we got was so 2 into m dash 1 2 is nothing but rotation moment of CD we got was 0.2726. So put that value 0.2726 and m dash of rotation moment of DC. No, there is no, we don't have rotation moment for DC, so keep it 0. So add these three, it will come out as minus 3.95 kilonewton into meter. Similarly for DC, 2 into rotation moment of DC we don't have, keep it as 0. So rotation moment of CD we got 0.2726, 0.2726. So add these three, it will come out as 3.27 kilonewton into meter. So this is how we need to calculate the final moment. We need to draw the bending moment diagram with the value of these final moments. So now we'll see. So I have already drawn the pre-body diagram of the problem. So this is the pre-body diagram of the point load which is not acting at the center, and this is the pre-body diagram of the point load which is acting at the center, and for CD is carrying the UDL. For that, pre-body diagram will come parabola like this. To find out this maximum height, we need to use this formula, substitute all the value, we will get the maximum height. So I have written here directly. So now we will see the net bending moment diagram. So our MAB value we got was minus 1.66. So minus 1.66 it comes here, and for our MBA value we got was 4.16. 4.16 it comes here, 4.16. This is 1.6, and our MCB value we got was 3.95. It comes here. MCB and MCD value we got was 3.95 and CD value is minus 3.94. both will coincide with each other, it will come here. Here also MBA and MBC value we got was 4.1, so both will get coincide with each other, only sign will change. Here also only answer is same, sign will change. So last our MDC value we got was 3.2. so it comes here 3.2. so now join all the lines. So this is our net bending moment diagram. This is how we need to draw. Here our problem ends. So if you like the video, like it, share it and subscribe for the more.